Ok, gracias por acompañarnos hoy. Tenemos con nosotros al señor Cristóbal Arrieta Pellegrini, que es doctor en Ciencias de la Ingeniería de la Pontificia Universidad Católica de Chile, y él trabaja en procesamiento de imágenes biomédicas, aplicaciones de imágenes por resonancia magnética, cuantificación de grasa hepática usando imágenes por resonancia magnética. Actualmente se desempeña como postdoc en el Centro de Imágenes Biomédicas de la UC, a través de un proyecto de postdoctorado. Cristóbal, la pantalla es toda tuya. Adelante, por favor.
Muchas gracias. Gracias por la invitación. Finalmente la presentación en inglés.
Estamos haciendo presentaciones en inglés para los alumnos de doctorado. Si quieres darla en inglés, ningún problema. En tu caso no es necesario porque no eres alumno de doctorado.
Bueno, entonces prefiero en castellano si es que no les complica. No, tal vez la voy a dar en inglés porque ya hice todas las slides en inglés.
Ya, me parece. Adelante entonces.
Okay, I'm going to switch to English now. So thank you for having me. I am Cristóbal Arrieta. Today I'm going to talk about MRI-based biomarkers for non-alcoholic fatty liver disease and why this is important. So basically, sorry, I'm going to minimize some Zoom windows here to correctly. Okay. So, fat facts. Obesity is related to several diseases. For example, diabetes type 2, cardio and neurovascular diseases, and cancer. And the projected rate of obesity by 2030 is about 30–40% in some cases. And importantly, non-alcoholic fatty liver disease is the more prevalent hepatic disease in Western countries, about 30% of prevalence. And its prevalence has been increased last decades, for example, from 18% in the 90s to 31% in the 2012. And the most important thing here is that in the presence of obesity, the prevalence of the NAFLD, non-alcoholic fatty liver disease, is about 80 or 90%. So in a few more years, we will have a really big problem. But interestingly, NAFLD has a really non-progression. It starts with steatosis, or just non-alcoholic fatty liver disease, which is basically an increase of intracellular fat in the hepatocytes. And in our body, we can find the fat as triglycerides. Then the next stage of the disease is basically considers inflammation, and then fibers of collagen, so fibrosis, and then we can have scarring, and some cells start to die, and we have cirrhosis, and eventually we can have also hepatocarcinoma. But interestingly, also, this disease is really reversible in the early stage. So it's really important to catch the disease at this early stage, especially in steatosis stage. Basically, the gold standard to diagnose the disease is the biopsy, which is invasive, and in some patients, for example, in patients with diabetes, it's a really risky procedure. But also, it's just a local sample, and we have a really big liver. And so MRI-based methods achieve non-invasive techniques in the first place, but also quantitative methods. So that's really important, because maybe this is our main contribution to the biomedical sciences, the ability to get quantitative methods for the, in our case, for example, for the radiologists. And between those quantitative methods, we can find spectroscopy, which basically we can see some peaks associated to different hydrogens of the fat. Fats are those really big chains of hydrogen. But the spectroscopy is also a local sample. It's just one voxel in the whole liver. So the water fat separation methods achieve what we can see here, which is a parametric map or a quantitative map in which each pixel corresponds to the amount of fat in the liver. And this map is called the proton density fat fraction, and is obtained by modeling the MR signal in this way. We will talk about this afterwards. So in this talk, I'm gonna present some basics on MRI acquisition, and then what happens in the presence of fat. Then we will study the water fat separation model, particularly the proton density fat fraction, which is this biomarker, really important biomarker. And then we will study other biomarkers related to liver. So in magnetic resonance, we have basically 4 steps to acquire an image: polarization, excitation, reading out the signal, and the reconstruction. So basically, the atoms with odd number of protons has this property, which is called the magnetic momentum, and we have a lot of hydrogen in our body. I mean, in the form of water. So normally the net magnetization of the body is 0. But if we put the body in an external magnetic fields, basically those hydrogens polarize, and finally a net magnetization different from 0 is generated. So if so that direction we normally call that direction as longitudinal direction. By using RF pulses, radio frequency pulses, we can take the longitudinal magnetization into the transverse plane. And when we turn off the radio frequency pulse, basically the hydrogen atoms go back to their stationary initial state. But in that process, they emit electromagnetic radiation, and we can measure that radiation basically putting a coil here. And so with that coil, we basically measure the integral of that signal. Moreover, but if we put some additional gradients during the reading of that signal, we can have this expression, this special expression. And if those gradients are linear gradients, what we have here is the Fourier transform of the signal. And that's a really important thing in magnetic resonance, because the object or the body can be reconstructed by computing the inverse Fourier transform of the signal. So what we acquire is the frequency domain. We call in magnetic resonance, we call it K space, because we are using that K variable. And then we can take the inverse Fourier transform, and we have here the image. If we look a little bit closer, a little bit deeper, we basically, if we turn on the RF signal, and then when we turn off, we can see that the hydrogen atoms or spins go back to their stationary state. And when we turn off the RF signal, we basically turn on the reading process. And we have here the integral of this magnetization. But if we, during the reading out process, we turn on those linear gradients, as I said before, we have here the integral of this quantity. So we basically are encoding the spatial information, slightly changing the frequency of the spins. So basically the frequency of this spin will be a slightly different frequency compared to this spin. And with this process, we can reconstruct the image. So what happens when fat is involved in this process? So the hydrogen of the water resonates a slightly different frequency than the hydrogen of fat. So we have a difference in frequency, I mean, naturally, without encoding any gradient. And when we turn on those linear gradients, what we have, we will have a certain ambiguity, because this spin of fat have a different frequency per se, and also it will have a changed frequency produced by the linear gradients. So what we see in the images is this artifact. So basically, we have here a kidney, and we have here, we can see fat, but the fat has a displacement in the image. And that's an artifact generated by the fat and by this property, which is called the chemical shift. But importantly, we know that shift, that difference in frequency, we know that. We know that is 3.4 parts per million. So we have here, we can see here the fat artifact. We see here this black line, and then we can see here a kind of zooming of the signal or overlapping with the water. So in the first place, fat was an artifact that we need to suppress. So there are techniques that can suppress the fat. And for example, if we have here a breast MRI, if we suppress the fat, we can detect this breast carcinoma. So it's very important. The fat suppression techniques are very important. But fat is not always an artifact. It's also a quantity that we want to measure. We want to quantify the amount of fat. And to do that, we can model the signal, the MR signal, because we know the difference in frequencies, in the resonance frequency between water and fat. So here we have the single peak model. Basically, this is the MR signal, and we can model the MR signal as the contribution of water, which is a complex quantity because it can have a phase. We have here the contribution of fat, the concentration of fat, corrected by the chemical shift, but this difference. And all this signal is modulated by this this variable which we call the field map, which basically represents the inhomogeneities of the main field. So the field is not perfect, so we need to add this variable to catch the imperfections. But more importantly, the fat doesn't have one peak. Because it has multiple hydrogens in this really long chain of hydrogen. So the fat has multiple hydrogen peaks, as we can see here in this spectroscopy. And we can add this information to our model. So we can have this is the first one is the single peak model, and the second one is the multi-peak model. And the multi-peak model has shown really good results, stable quantification of fat. And so it's really important I mean, starting from the single peak model, we can understand the multi-peak model. So basically, the fat is not only one peak, it's a collection of peaks where here the omega correspond to the relative amplitudes of those peaks, and the F under P is are the frequencies of those peaks. But in the model, we assume that this is known. In fact, we can obtain this from a spectroscopy. So we have now a better model with exactly the same numbers of unknowns. And this is, well, if we solve this model, there's a detail here, really important. So here we have the MR signal depending on the time. So if we have only one acquisition, I mean an acquisition at certain time, we cannot solve this inverse problem. So we need to acquire a collection of times that we call echo times. So with different several echo times, we can solve this this inverse problem. And I mean, in this case, we can have at least 5 echo times to recover those unknowns, because we have here 2 complex unknowns. This field map is a real unknown. So if we solve the problem, we can have an image that represents the concentration of water and an image that represents the concentration of fats. Here we are actually looking the magnitude of those images. And with those images, we can compute the proton density fat fraction, which is basically the amount of fat divided by the sum of water and fat. And we can see here these parametric maps in which as I said before, each pixel represents the amount of fat of the liver in this case. So we have here a mild liver steatosis patient with fat around 10%. And we have here a severe liver steatosis patient with amounts of fats near 30% or more. So the proton density fat fraction has been exhaustively validated in phantoms, animal models, patients, in comparison with spectroscopy, in multi-centers, multiple scanner brands, and different protocol, different sequences, different algorithms to solve this linear problem. And the conclusion is that it has a really high precision and reproducibility to quantify the steatosis grade, and it can detect changes about 1%. So some authors have proposed that finally the PDFF can replace the biopsy. However, as this sentence expressed here, the PDFF is really good for the steatosis grade. However, to follow up the progression of NAFL, the PDFF is not enough. So the PDFF is really, really useful for the steatosis stage. And this is because early detection of the diseases is probably the more important, one of the more important tasks for us as biomedical engineers. But so the PDFF is a really important contribution to the area. However, we need to follow up the patients. We need to really detect when all the other processes start. So we need to look into other biomarkers. And one of those biomarkers is T2 star. So T2 star is basically the signal decay, because we sample the MR image in different echo times. So, well, we have the water and fat evolution, the inhomogeneities, but we also have a signal decay. And we need to consider that in order to have a robust model. But also, if we introduce the variable R2 star, which is the signal decay, this variable is really, it has information. It has valuable information for some diseases or some conditions. And it's really easy to add to the previous model. So we basically, now we have this variable as a complex variable, and the real part will be the field map, and the imaginary part will be the signal decay. So in the first place, if we see here a proton density fraction that considers T2 star in the model, get to better values, to more accurate values of fat, compared with a model that doesn't have the R2 star or T2 star. I mean, T2 star is the reciprocal of R2 star. But more importantly, T2 T2 star can also be used to measure the liver iron concentration, which is a really important quantity in some diseases. And so you can have a conversion between T2 star and the liver iron concentration. However, that conversion is not easy to implement. It's not easy to find. The experience by now is that this calibration curve depends a lot on the experimental setting, the main field, I mean 1.5 Tesla or 3 Tesla, or even the vendor, the brand of the scanner, so that there are differences. But it basically is like a center-dependent curve of calibration. And well, now T2 star is in this validation process, similar to the PDFF, and we have now studies running to really measure what are the normal or the healthy values for T2 star in the liver. And we have here, for example, a really interesting study in the UK Biobank. But the validation process is more complex than the PDFF. Firstly, because there is no easy way to generate a phantom to calibrate the T2 star. And also, if you change the protocol, for example, if you change the number of echoes that you acquire, you have a slightly different values for T2 star. And more importantly, T2 star is very sensitive to the signal to noise ratio, which can be affected by several parameters in magnetic resonance, for example, the resolution. But importantly, this signal to noise ratio depends on this number of averages. So in magnetic resonance, in order to increase the signal to noise ratio, we basically acquire several times the same information, and then we take the average of that signal. For if we acquire chest images or liver images, in order to avoid the respiratory motion, which can cause artifact, we ask the patient that for a breath hold. So basically the acquisitions can't be as long as maybe as long as the good signal to noise ratio requirements can be fulfilled. So in several cases we take a more reduced number of averages of the signal, and we will have a noisy signal, basically. So for the T2 star, we have clinical recommendations in order to have enough information to calculate the T2 star. Some authors recommend 8 to 12 echoes. So this is a lot of echoes compared to the 5 echoes that we needed before. But also we need to take care of this number of averages. And in that sense, we propose a really new formulation for this water and fat separation problem, in which we can add regularization for the R2 star. Basically, we can add denoising for R2 star, so we can deal with critical situations, or we can deal with lower signal to noise ratio. And so our new robust formulation that we call reduced ideal is based on a matrix formulation of the model. So we have here again, the initial model, we have the amount of water, the amount of fat, the multi-peak spectrum of the fat, and here we have the field map and the signal decay R2 star. We can write this expression as with a matrix formulation, and we use basically this W diagonal matrix that has these variables, the field map and the R2 star. And we have the matrix M that basically has the fat model here. But importantly, it's really important to note that rho, or in rho, this problem is linear. But of course, this term is highly nonlinear. But we can, if we assume that we have this chi, we can obtain rho by solving a linear least square problem. And if we replace this expression in the initial model, basically we can factorize and get to a new expression, which is based on the pseudo inverse of M. And we have now this P operator, and we can solve the problem minimizing P times S square norm of that. So that's the first contribution that we proposed in this work. However, if we compute basically the naive solution of those of that problem, that now it only depends on the chi variable, we can have those famous in this area, those water fat swaps. So we have basically a solution in which in some point water and fat are swapped. And that's because we have here an exponential which has multiple solutions. So we firstly need to add a regularization for the field map, because if we regularize the field map, if we impose a smooth field map, we can avoid those jumps, those wraps in the phase. And then we set the R2 star, which is the imaginary part of chi, as a positive quantity. And we can also add denoising to the R2 star, which is basically what. So we have here the model, the P operator times S, and a denoising for the R2 star, non-negative constraint for R2 star, and a smooth constraint for the field map. And we can solve this problem by using ADMM and have really interesting results. But also in cases with extremely low SNR, we can also add a regularization or denoising for the signal. So this framework, the framework that we propose, is really flexible and allows us to also add denoising to the signal. So we have here basically denoising to the parametric map R2 star or T2 star, denoising for the signal. Well, this is a constraint for the denoising, that the signal needs to be similar, as close as possible compared to the original acquisition. And the results are, we can see here the results. So this graph cuts T2 star is basically the gold standard now for computing the water fat separation problem. And we can see here that we have a proton density fat fraction and a noisy proton density fat fraction, and also a T2 star map, a noisy T2 star map, With reduced ideal, we have, of course, a noisy proton density fat fraction because we don't have the noise in the signal, and also, but now we have a smoother T2 star. And for the last formulation, we have here that we have basically a denoised signal. So we have a proton density fat fraction with a better quality or a denoised proton density fat fraction. And also we have a smoother T2 star, which is basically in between these two solutions, the gold standard and the reduced ideal one. So we validate our approach with 12 volunteers, and so what we see here is that we have in these plots, these Bland-Altman plots, we have the NSA, the number of averages equal to 4, and our gold standard is a 12 echo acquisition, which is the best recommendation that authors have proposed. So we have a 12 echoes acquisition with NSA equal to 4. That's our gold standard, or that's our ground truth. And we compare the graph cuts, which is the gold standard, the same algorithm, using the same signal to noise ratio, NSA equal to 4, but now with 6 echoes. So we are reducing the echoes, the number of echoes from 12 to 6. And what we see is that the proton density fat fraction is quite accurate. I mean, the errors are less than 1%. And we have here a T2 star, which is really good, actually. So we have a low bias, about 2 milliseconds, and here we have like a 5 milliseconds of confidence interval. But if we reduce the number of average from 4 to 2, what we have is a worst proton density fat fraction, but still good. I mean, it's about 2% the interval of confidence. However, the T2 star has a 4 milliseconds of bias and a really high dispersion. And if we add our regularization, the approach, our regularized approach, we have a proton density fat fraction which is a little better than the ground truth. Than the gold standard, but the T2 star is quite comparable to NSA equal to 4. So we have a T2 star comparable to have twice the information, twice the acquisition, or twice the signal to noise ratio. And if we look at the dispersion inside the region of interest, we can see here that for the gold standard, 6 echoes NSA2, we have this dispersion, and with our approach, we reduce the dispersion dramatically. So this is, and because we have a really good or really accurate results, we can say that our approach is more reliable. So just in the last minutes, I just want to quickly comment about this final application that we were working that we're working on, which is called magnetic resonance fingerprinting. And the same idea here. We need more biomarkers to really have more information in this stage of the disease. And magnetic resonance fingerprinting is probably the best way to obtain that. So what is magnetic resonance fingerprinting? In magnetic resonance, we normally acquire in this fashion. So we basically wait until the signal is really ordered and the spins are allows us to acquire in a really precise times or precise moments in order to have contrast. I mean, in order to differentiate tissues. But if we have this situation on the right, basically we have the same amount of information, but in a more random way put here. So in magnetic resonance, there are some special sequences that acquire the images highly undersampled and with several artifacts, for example, noise and also blurring. So we can see here a fully sampled image. And if we undersample the image in some particular ways, we can have those kind of images which are really bad to try to diagnose with that images. But the important thing is that it retains or it has information. So in the last year we have a lot of algorithms to denoise and blur the images, and we can use those algorithms. So using those kind of acquisition of really undersampled acquisition and using algorithms to the noise and the blurring, to the noising and the blurring, and also if we combine those techniques with dictionaries, we can compute parametric maps, quantitative maps, by using those kind of acquisition, which are really rapid to fast to be acquired. And the idea of dictionaries is that there's just a set of values of biological plausible values in all those maps. So we simulate the MR differential equations produced by this special sequence, and we can have several fingerprints by changing the possible or the plausible biological values of those parameters. And then we basically match, we find the best match of the acquired signal compared to the dictionary. And we can have those beautiful quantitative maps. So this is called magnetic resonance fingerprinting. And we can combine those techniques with water and fat separation, and we basically can compute a lot of maps in the same acquisition. So in just one acquisition of about 14 seconds, we can have one slice. We can one slice, but with several maps. I mean, the T1 map, the T2 map, the T2 star map, which is here, and also the fat fraction, just in simultaneously in one acquisition. And that kind that kind of techniques are basically probably the state of the art, or are in the most advanced techniques, which are by now not clinically available, but are in the research area. Well, we published this technique in a collaboration with KCL. Basically, we compared phantoms and 12 volunteers. And again, with one acquisition, 14 seconds, we can have for each subject, T1 map, T2 map, T2 star map, fat fraction. So we at least need normally 3 acquisition, 142, 141, 142, and 142 star, and proton density fat fraction, as we studied already. So we need at least 3 different acquisition, and now in just one simultaneous acquisition, we can have these maps. So this technique are very important and will be very important in the next years. So in summary, we have this NAFL, this non-alcoholic fatty liver disease, which has a lot of stages. And we firstly study this proton density fat fraction, which is really good to diagnose the early stage of the non-alcoholic fatty liver disease, the steatosis. And then if we want to follow up the next stages of the disease, we need additional maps. So one technique is add T2 star to the water fat separation, but we now have also this magnetic resonance fingerprinting available, which can obtain several maps in just one acquisition. So thanks a lot to my funding, to the professors, and also thank you for listening and for the invitation.
Thanks, Cristobal. I'll stop recording now.